Yeah, so let's start. It's currently recording. So today I'll go over the exam. You guys completed that, right? So we'll go over just the answers to the exam, and then after that, we'll talk about the multi-layer perceptron, okay? Which was the thing that we had. So I think I had said that if you have questions about Keras or the project TensorFlow in general, that you should bring the questions today. Let's actually go over calendar for a second just to see where we are in the project or in the semester. So let me open up calendar. There's the screen. Calendar. So everyone's recording. All right, so you should be seeing the calendar. Let's go to the course website. So foundations. Refresh just in case. All right, so we saw deep learning with TensorFlow. This was the video, I believe, from April 13th. Okay, this is an older one. I haven't updated. All right, so I'll need to update that, but I think here. Okay. All right, yeah, so we are currently on April 11th. Oh, that's right. So we did Keras here, and then I switched these around. That's what it is. That's fine. Okay, so we did last week, we kind of went over logistic regression, right? And linear regression. And then instead of doing multi-layer perceptron, we just went into Keras, correct? So that was on April 6th. So then that was it. If you remember, I mean, we kind of went over it. So really, I just did that so that you had basically code that you could start using for your term project. How many of you have started using that for the project already? No? Right. How about you guys? Are there any questions? Okay, Lenny. All right, yeah, good. So, make sure that you start working on it so that you have any questions. As you can see, we're almost at the end of the semester. Jello works well. Ah, wow, that's good. That's interesting. So I'd be interested to see that. Good, good. All right. So yeah, so April 6th. That was last week. April 13th, that's today. We really just have the multi-layer perceptron. I'm going to talk about that today. We had the exam, obviously, on Monday. I'll go over the solutions, basically. Then we really just have like one lecture left, right? Which will be the lecture of April 18th. My plan is on April 20th is just to, I want to see your projects. So, because on April 25th, you guys will do your project presentations. Okay, so we'll reserve that time. You'll get like 15 to 20 minutes, whatever you need. We're a small group, right? And so the plan is, you can see in the calendar here, I do want you guys to come to class and just come up here to the podium and just kind of do your, the way that we've always done. Right? So do your presentations, but that's why on the 20th, I kind of want to see your projects, just be, so I can give you any pointers or whatever, see where it is before the presentation on the 25th. And then you have almost a week still. And then on April 27th, I'll just do a course wrap up. Any topics that I haven't covered, I'll throw in there. But we've pretty much covered everything at this point in the semester. We covered, I usually do like distance metric based things. We start with that, then probabilistic. We did that, and then neural nets. And we've come to the conclusion of neural nets pretty much today. So what I probably will do on April 18th is I will do clustering maybe or something like that on supervised learning. So we'll talk about that. But really at this point, I'm pretty happy I've covered all the main areas. Are there any questions about that, guys? Project or otherwise? No? All right, so let's take a look at the exam then. This portion I'm not going to record, just stay in the Zoom session. So let's just do, I'm gonna, all right, so I'm recording now. I'll start a Jupyter notebook. All right, so Jupyter notebooks are starting. All right, and then let me just go to the course folder. 2022. Yeah, and so I'm just going to create a new Python script. I'm going to call this multi-layer perceptron. Right, so this will be the last topic of neural nets. We'll wrap it up here. Let me just rename this. MLP. From scratch, I guess, as much as possible. So the idea with today's script is I would not recommend that you use this script to solve any problems, right? It's mostly, that's why I've left it for the last thing. It's mainly just for us to have a discussion of the different concepts and ideas of neural nets. Last week, I gave you examples of Keras, and Keras is definitely the way that you should tackle this problem. First of all, the code that we're going to write from scratch is only a multi-layer perceptron, which means it's only an input layer, an output layer, and a hidden layer. And a lot of work goes into getting that to work, just as that one script with that architecture is not very flexible, etc. Whereas in Keras and TensorFlow, you can create that in a matter of minutes, right? You can get your TensorFlow algorithm to work really well, and not only an MLP, but you can do from logistic regression all the way to a deep neural network, CNNs, whatever it is that you want to do, right? So you can do all of those. Oh, it's not sharing? Yeah. Oh, sorry. Okay, so I'm going to go ahead and share the screen. So, but, I feel since for completion, from the beginning of the semester, the whole course has been in NumPy, right? We've done pretty much everything in NumPy, all the traditional algorithms that were distance-based, all the algorithms that were probabilistic, like naive Bayes, hidden Markov models, etc. And now the third phase, we've looked at a lot of algorithms, perceptron, linear regression, logistic regression, from the point of view of NumPy and from scratch as much as possible. So now we're going to do the MLP. This is that algorithm that you guys would run in Weka, and it was really slow. Now you can create these in TensorFlow, and it's really fast. And that's definitely, as I said, the recommended way of doing it. But we are going to go through, just as a nice exercise, I think, how to lay out MLP. And that will be pretty much the last discussion of neural nets this semester. Okay, so let me go find my code. All right, so we're going to need some libraries. I'll start with a few functions. just to kind of lay them out, some of the terminology that you already know about. And then we're going to think of some of the parameters that go into it, some of the architecture that needs to go into it. So it's quite extensive, actually. As usual, I mean, this code is already on GitHub, so you can just get it from there. It's the multi-layer perceptron, but I'm kind of just, since I'm discussing, I'll kind of type it out. So yeah, so let's go ahead. First of all, let's just think the big picture, right? So we have the big picture of our algorithm. We're going to create a class for this, given that, you know, an object-oriented, we're going to take an object-oriented approach just because it's such a complex thing, right? So to try to organize it a little bit. But let's kind of think about what we need here. So I'm sharing the screen. We have plenty of time, I think. And then whatever I don't type up, we can just copy it from the GitHub. All right, so let's go ahead and get started. We're going to need some libraries, so I'm going to import. I'm going to import NumPy as NP. Okay. Import math. I'm going to then sklearn. sklearn, import data sets from sklearn dot model selection, import train test. Okay, so those are just the libraries to get those out of the way. Now I'm going to start listing out basically some of the functions that we would need. So one thing that you should always do with your data is you should always normalize it. Okay, so I'm going to define a function, define normalize. Now what's so great about using frameworks like Keras is, of course, the code in Keras is written like this in the background, but we don't actually have to even look at it. We just bring in the function that normalizes, whenever we want to. So this is one. Just say return 0. So that's a function. And then we are going to the one-hot encoding approach here. So that's define to categorical. So that's another function that we can use. So this one is to convert something from normal labels, let's say labels like 0, 1, 2, to possibly something that looks like, for 0, it would be a vector of 1, 0, 0. You see that? That's called one-hot encoding. And this is an approach that becomes very useful in machine learning. So one-hot, with neural networks in particular, one-hot. Okay, so the categorical function would convert basically to that. So we're going to say return one-hot. Right, so your one-hot encoded vector. All right, then we're going to do okay. So the next one is our accuracy function that we've been using all semester. So I'm going to do define accuracy score. Define accuracy score. And then here we're just going to say return accuracy. So some of these we can just recycle from previous code. That's what's so great about it. All right, then we have a few things that we're going to need, like the cross entropy function. So we can actually define that function. Now it is probably not recommended it's good to like try it out once and kind of get a feel for these functions initially. But when you start doing TensorFlow or PyTorch, it is always recommended to use the built-in functions. So those libraries actually will have a function just called cross entropy that takes inputs, parameters, etc. But you don't actually see the equation itself, right? Like the one I have in the PDF. Here, we're just for the sake of having something and looking at it, we'll do it, but it's already in their code, but it's definitely not recommended. Because you can end up with problems like underflow divisions, where you divide by very tiny numbers, which are basically zeros, and they give you like nans, not a number. And so that can happen. And so the functions control for that really well. And so it's definitely not recommended, but if you're curious about the functions once, it's good to look at. So that's the class cross entropy. So we can take a look at that one and define a few things for it. Then we're also going to need, as a cross entropy, we're going to need the class sigmoid. We're in a class here. Yeah. Just quiet, if you're quiet. Yeah. Right, and so if you have the function sigmoid, so we can define that one as well. So sigmoid. Okay, so the sigmoid function, as you know, this is the activation function. So basically the behavior of it is to map any value to values between 0 and 1. Okay, so that's going to be, let's call it activation function. All of these are going to be defined basically here. Okay. And we can think about, right. So then the next function that we're going to define is the softmax. Remember that the softmax was also a slightly better function than the sigmoid because all values add up to 1. So that's a function we can use here. So I'm going to do, this is also going to be a class, an object. So I'm going to say class softmax. Okay, and we're going to define it basically. Then we can, if we want, we can actually define a class for the multi-layer perceptron itself. So I'm going to do class multi-layer perceptron. Okay, so the multi-layer perceptron, this would be the object for it. Is such a complicated structure, which will have a lot of variables that you need to initialize, etc. So we'll probably create an init function to have those parameters, and then inside of it, we'll need to define the fit function, which is usually the heart of what we're doing. Okay. And also we're going to have a predict function in there. And then that should be it as far as like defining the algorithm. Then after that just comes reading in the data, right, and processing it. So let's kind of lay that out in like our main section. I'm going to go over here. Okay, so we've got our, let's start with the data set. So we're going to do data sets. And then we're going to say, because we called in data sets from sklearn. So we're just going to read some data. We're going to say load digits. Okay, and we can always print this out. We've got our X data here. So that's going to be data. We're going to normalize this. So normalize, that's a good question that I could ask on the exam, right? What does normalize mean? And you guys remember when you had values that were really big and values that were really small, You just make all of them in the range from 0 to 1, so that all the axes in the vector space are the same size. You don't have one dominant feature. Does that make sense? Yeah. I know we've talked about it. Just remember it. So I could put that on the exam. All right. So that's, we've got some data here available. And then we have the labels. This is still supervised learning for this neural net. So data dot target. Okay. All right. So that's kind of where we are. Then you want to convert the labels, which are probably going to be, as I said, 0, 1, 2, whatever it is, to one-hot encoding. So usually a lot of machine learning, whenever you get into like deep learning, et cetera, you always one-hot encode your vectors, everything. Okay, so we're going to use that one-hot function. So let's just say convert the nominal y values to binary. So we're going to convert them. So that's going to be y equal to categorical. I should have just called this one hot. That function is so important that TensorFlow has its built-in functions called one hot encoding. So it's all of these functions, they already exist. And we never see the insights of them. So that's why it's kind of nice to at least once go through it. Remind ourselves, if anything. All right, now we're going to take the data and we're going to split it. So we're going to do X train, X test, Y train, Y test. Okay, so we're going to take these. We're going to run train test function. Train test split, actually. And train test split will take X, comma, Y. And the test size, the usual equals 0.2. Okay. Okay, so we have random state. Okay, and just any value is fine. Okay, so now we have our data ready. So the next step then is to initialize an object, right? So if you remember in Keras, we did model, right? And we always do something like that. Well, this is how it works, right? So here I'm just going to create, an object, let's call it CLF, whatever. But it's going to be an object that is going to represent the neural net. So the MLP. You can call it whatever you want. This would call the class multilayer. So this will call the class multilayer perceptron, right? Which is the class that we have yet to define here, right? But that's the class that we're calling. So CLF multilayer perceptron. That class will take certain parameters, so we can just define them here in a similar way to how we did it in Keras as well with TensorFlow. So here I'm going to say, for instance, that the hidden is going to be 16. So n hidden, and we need to define that parameter. It's going to be equal to 16. We need to define that. We're going to do a fitting. So the training. So we're going to define the number of iterations. And iterations. So let's just plug in a value in here, whatever we want. Let's say 1,000. And iterations, the learning rate is going to be some value. Remember that the learning rate is pretty important. So 0.001 or 0.01 seem to be good ones. Okay, so learning rate. All right, once we have that, we call CLF dot fit, and we're going to train it on X train and Y. Okay, so this is just a standard approach that we've always taken, but we need to define these now from scratch. Once we fit the data, then we're going to predict. So I'm going to do CLF dot predict. You predict on the X data, so X test. Okay, and let's just call that and that's the predicted data. Predicted vector, actually. So that's our predicted vector. So now this is a vector of all the values that were assigned to all the different classes, right? So, but we need to still select the highest value, right? Like the highest probability that it's a cat or a dog. Yeah, go ahead. We'll define it in a second. So N hidden is probably the number of neurons in the hidden layer. So we'll define it in a second. All right. So let's go ahead and do the selection of predicted vector. So I'm going to do YPred. That to do this, I need from numpy.argmax. Right. So I'm going to do an argmax of the predicted vector. Remember that argmax returns the index of the highest value in the vector. So if cat had a value of 0.8 and that's the highest, then and that's the third node, and it's going to return 0, 1, 2. Right? So I'm going to do NP argmax of predicted vector. Okay, and now I have the index YPred. Now I'm going to do the same for the label data. So I'm going to do YTest equal np.argmax of YTest. NP argmax of YTest. And because this is a matrix, there's the 0 and the 1 axis. So we want this across the 1 axis. So it's going to be axis equal 1. All right. And now we have YPred and YTest. So we can actually compare these two with our accuracy function. So we're going to go ahead and do that and calculate accuracy. So accuracy will be equal to the accuracy score function, which takes YTest and YPred. Takes YTest, YPred. Okay, so it takes these two, YTest and YPred. And now we would just basically print out the results. So in this case, accuracy. Okay. Yeah. All right. So that would be the entire pipeline for this to work. We went from the data, right, to the data set, from the data sets to normalize the data, to converting the Y vector into one-hot encoding, split the data, and then after that, we call our perceptron basically algorithm, class object, and we fit the data first, we train, and then we predict on the X test data, and then those results are compared. So now we are ready to define all of these functions. And as I said, we're going to do that from scratch. So let's start with the main function, which is, or the main class, which is the multilayer perceptron. So this is how you define a class in Python. And now in here, we're going to define individual functions that we want to use. So we're going to say the first one is the standard define init function. So that has 2 underscores in the front, and init, and then 2 underscores. And that's just like a reserved function that's available in the Python classes. All right, and so every time we instantiate a new multilayer perceptron, we have basically this this way of creating things. So we're going to add parentheses here and the colon at the end. Remember that you plug in the word self, which is the object that kind of refers to that instance itself. So when you define objects, then we have the things that we were passing, right? Which is n hidden, and also n iterations. Which in this case, we defined n iterations to be 1,000. And we pass the learning rates. Okay, so that's the init function. So now we can call the self object. So self.nHidden. Hidden. Okay, and that's going to be equal to the nHidden value. So we're just, making this available. It's really hot in here, isn't it? Yeah. All right. Then we're going to do self dot n iterations. Okay, and that's also the parameter n iterations that we just passed to this class. Okay, and then also the learning rate. So we're going to do, and then here I have a little typo. So just pay attention to these little typos. So self dot learning rate. That's just a parameter that we're passing as well. Okay. Additionally to that, we want to define a couple of things that are usually associated with this object, right? With multi-layer perceptron. So they're going to be the loss function, the activation function for the hidden layer, and then the activation function for the output layer. Right? So you guys should know what that means, right? So you guys will tell me, but let's just, so we need these three parameters. So I'm going to do self.hidden activation. So that's the activation for the hidden layer, not the last layer. Then we also need the self dot output activation. So for the last layer. Okay. And then we're also going to define the loss function. So that's going to be something else. So what are these? Let's start with the loss function. What is the function for the loss function? What's the name of it? Cross entropy. All right, good. So we need to define cross entropy, but we're just going to link it here. So cross entropy. What is the activation for the output? No. For the output. Softmax, very good. So softmax, exactly. Softmax. And then what about for the hidden? ReLU. And we can do ReLU. ReLU is actually a function as well. So we can do it here. I'll just put in sigmoid right now, but it's actually a really nice exercise to think about how this one works. I'm going to do here class. And it's actually a very simple function, simpler than we would think. But for now, let's just say it is the sigmoid. Okay, so we've got basically, we have at this point the variables that we need, everything associated with the class, just to make it straightforward. The next step that we need to do is we need to define three functions, right? We need the function to fit the function to predict, and the function to initialize to parameters. So let's just say, let's just list these functions. I'm going to do define initialize weights. I'm going to initialize the weights. Again, this is going to be self, right? And we're going to have to think of the parameters that initialize weights will take. Another function that we're going to do is fit. That's the training function. Define fit. Again, it'll take self. To train, this one takes x comma y, right? So it takes those parameters to be able to do the training. And then we're going to do predict. I'll do define, predict, and predict will take self and also the, the test data in this case. So we can just call it X, basically. All right, so once we have this, we can start plugging in the values. So let's probably start with the easiest one. So I think predict is the easiest one because we just have to take the data and multiply it times the trained parameters, right? So the trained parameters in this model are going to be what? The weights and the bias, correct? The W's and the B's. So here I'm going to do hidden input, let's say, which is going to be equal to that original X that I got here. And I'm going to do a dot product. So I'm going to invoke dot dot. Remember, we've talked about the dot product as a way that we can multiply a matrix times a vector. In this case, the vector is the weights times this. This assumes, remember, in predict, we assume that we've already trained the weights, or maybe not, but we have a vector of weights and biases. If they're not trained, it gives us basically wrong answers, but it can already make predictions. So I'm going to do hidden input X dot, and then in here self dot W. Now we haven't defined self W yet, but we will, right? So those are the weights. So I'm going to do uppercase W here. And then I'm also going to add to it plus the bias parameter, which is self dot, and let's call it W0. Okay. So I have that here. Now, because this is a multi-layer perceptron, it needs to have one layer, another layer, and another layer, right? So here, if you notice, we started with X, right? Do you guys agree that we started with X? So then we have X and the weights, and that gives us the first hidden layer. So hidden input is the first one. So what I mean by that is if we go to the whiteboard, so far we've done this part and this part, right? With the weights. That's what I've done. But I still need this other part, okay? So that's going to be the second layer. So that's why this one is called hidden output, basically. So that means hidden here. And then, so this is hidden output. And this one we can probably just call output. So this one we can just call output there. All right, so I'm going to go ahead and go back to the code. And really, this is one of the most important parts because it relates to the architecture itself. The other functions, we can just literally like copy them. So we have hidden input. Now, hidden input needs to go through the activation function, right? So we're going to call that hidden output now. But what that means is that hidden input goes in this function, right? And this function is going to be from self, this object dot, we're going to call what? Which activation do we call? And what is that call in our object? It's the hidden activation, right? All right, so hidden activation. Okay, that's the layer now with its activation. So it's now gone from linear to nonlinear. Remember, this is linear, this is nonlinear. Okay, so then I'm going to take the next one. I'm just going to say output layer input. Again, this one is input because it needs to go through the activation. So this is just going to be the hidden output. Dot. So we're going to do the dot product. And this time around, it's going to be with another set of weights, right? The weights that go in this part here. So these weights, right? So we're going to have to give those a separate set of names, right? So let's go ahead and do that. Here we're going to say hidden output dot dot self dot v instead of w, right? Just another name that we're giving it, and this also has a bias. So let's do plus self dot v lowercase 0, just to be consistent, and that indicates the bias for that second set of layers. You can see how we've literally written out all the weights, right? That's, imagine if you're building a deep neural net of many layers, you'd have to do this every time. So it's not practical. Now we have, we're ready to do YPred. We just need to run it through the softmax. So YPred is going to be equal to self dot output layer input. Oh, sorry, output. Output layer input actually. So it's going to be self, or no, just a variable output layer input. So that's the one, but we need to run that through the activation function. So in this case, softmax. So I'm going to do here self dot output activation. Yep. And open parentheses, close parentheses. So self output activation, as you can see, that's just softmax. All right, and then now we are finished and we can just return YPred. Any questions about any of that? Questions making sense? Yeah, so that's YPred. As you might imagine, fit will be a little bit similar, except that we need to have the update, right? We need to have the update rule in fit, but fit also needs to do a little bit of that. So let's go now to the initialize weights, because we need to initialize these things that we've been talking about. So let's go to this function here. Okay, so let's go to the code. All right, and we're going to define here the initialize weights function. So for this one, we said we need X and Y, probably because we're going to need the parameters, right? So we need the sizes and everything to figure this out. So it's going to be for initialize weights, X, comma, Y. All right. And so now we need to know the number of samples. So I'm going to do n samples. N samples. I'm also going to do n features. All right. So I know the size of the input vector. I'm going to call x, and I'm going to do shape, and that should return those values. Okay. So that should return those values. All right, then we also need for y, the shape. So we just need to know the number of columns, which because it's one hot encoded, we're going to know the number of classes. So I'm going to do underscore comma n outputs. Okay, and I'm going to call y dot shape. All right, so I've got my measurements. Now I'm going to go ahead and initialize the weights and the biases for the the first set of from input to first hidden layer, and the weights and the biases from the hidden layer to the output. Okay, so the first one, let's just call it hidden layer. Okay, so I'm going to do hidden layer. Okay, so hidden layer. We need to initialize these variables here. So I'm going to do self dot all right, so yeah, so I'm going to do self. Where was I? Yeah, W. Okay, we're going to initialize this. Also self dot W0. Okay, so that's going to be the weights and the bias between the input and the first hidden layer. Okay, so to initialize it, we're going to use NumPy. So NP random. Instead of we could do zeros, right? We could do zeros, but here I'm just going to do np dot random dot uniform. Okay, so np dot random dot uniform, and we can specify some values here and the size of the matrix. So here I'm just going to say negative limit to positive limit, and then we're going to specify the dimensions, which is going to be, what are the dimensions here for this matrix? This is an important concept to know. This is the matrix of weights between the input and the hidden layer, right? So what do you guys think should be the dimensions? What should go here as far as the variables? So this is what? N features, right? So the number of features that you have in that X vector. And then this is going to be N hidden, the number of neurons in that hidden layer. So we can do here. We already have, that's a parameter that we define in the class. So we do self dot N hidden, like this. All right. And now the question is, what is this limit? So limit is just going to be a value that we're going to calculate based on the number of features. So this is, I'm just going to plug this in. It's just like a formula that was worked out to provide better values than, let's just say, random values. So I'm going to do square root here. And this square root is going to be based on N features. Okay, there's various ways of initializing the values of these, and this is just one approach. All right, and then for the biases, those usually don't need so much logic to initialize them, so we can just use np dot zeros. Okay. And now we're going to say that this is also a vector, so it's size 1 by n outputs. So basically that's the size of it. All right, which is in this case the size of the class, basically. Now we do the same thing. Oh, sorry, no, wait a minute. This is, no, it should be n hidden. Excuse me. This should be self dot n hidden. Like that. And if you think about it, that kind of makes sense because we are in the, if you go back to the whiteboard, you can see here, if we have 3 neurons in n hidden, right? We have 3 neurons here, then that vector is plus, plus, plus W0, W0, W0. Therefore, the size of it should be these 3. Does that make sense? Yeah. Whereas this one, if there's 5 here and 3 here, that matrix, the W matrix should be 1, 2, 3, 4, 5 for these 5, and then 1, 2, 3 for these 3, right? Because it's that matrix. So it's a matrix of 5 by 3, and this is a vector of just 3, the 3 biases that get added to that. So that's why it should be hidden, n hidden is the value in the parameter there. Any questions about that? That make sense? All right, so let's go back to the code here. So we did this, and that's in hidden. Now we do the other set of parameters, which is going to be just get this. All right, so the other set of parameters is going to be for the output layer. Output layer. And so that we're going to copy this, but this time instead of n features, we're going to use n hidden. So I'm just going to plug that in here. So this is n hidden. 1 math square root, same thing. This is just for the initialization. And then I'm going to do self dot b. And it's going to be here, the same, kind of the same thing. We're just going to copy this, but change the dimensions a little. So self v, np random uniform, limit. This is now not n features to n hidden, but n hidden to n outputs. Right, so it's going to be here self dot n hidden, and then this one is no longer n hidden, but it's out and outputs. The number of classes, which is this value that we calculated here. Assuming we've already one-hot encoded that. So that's n outputs. Okay, we've got the dimensions for that vector, and then we just need to do the biases again, which is going to be V0. And that's NP numpy dot zeros. Okay. So we specify the dimensions as a tuple. So that's 1, comma, n out. Okay, so that's basically the initialization of the parameters. And now we are ready to just look at the fit function. Okay, which is a little bit, more complex, obviously. From the fit function, we can call the initialize weights function. So I'm just going to do self. Every time we're going to fit, we reinitialize the parameters, basically, right? So the first thing we can do here is we do self initialize weights. Initialize weights, and that will basically call this function, and all those parameters get basically created, right? So we have now, you can think of it as we have now the variables that will store the weights and the biases for the architecture, and we just have to link them together. I'm going to go over here. So initialize weights takes X and Y. We were already passing those parameters, and so that works really well. Okay. Now, in the fit function, what we need to do is we need to iterate through the algorithm over and over and be able to do the training, basically. So here I'm going to do a for loop. So for I in range. And we're going to specify the number of iterations by calling self dot n iterations. Okay, so we're going to call by the number of iterations, and now we're just going to do three things. And okay, forward pass, backward pass, and update. Right. So if you remember, it's like feed forward, right, and then back prop, and the back prop does. But we're going to do it not in a super efficient way. Instead, we're just kind of take what we've been doing with the perceptron and all the other ones, and just kind of do it like that, right? But this should capture a lot of the ideas and the logic of our neural net. So now I'm going to do the forward pass in the for loop. So I'm going to do forward pass. Okay. And then we're going to do a backward pass. Let's do here. Backward pass. Backward pass. And then we're going to do the updates. So update the weights. The update rule. So let's just say update the weights or the parameters, which are the weights and the biases. Okay. So that's the idea here. So let's keep going. So we're going to go through the forward pass, and we have to kind of define. Let me save this before So the forward pass is basically just doing the multiplications. That's literally it, right? So it's almost what we have in predict. So let's actually copy it, right? So I'm going to copy that from predict. I'm betting it's pretty much this. And then we can just modify it. Okay. Just make sure the alignment is correct. Okay, so this is the first hidden layer, and then this is the output layer, right? So let's do hidden input. That's going to be x dot self w plus self w0, right? That's exactly what we did before. Then that hidden input goes through the self dot hidden activation, and that gives us hidden output, all right? That's from input to hidden layer. So again, if we go to the whiteboard, That's this part here, right? So we've done that part. And now I'm going to do this part. So I'm going to go back to the code. Right, and now we focus on this as that second part. So that's going to be, we're going to take this one, hidden output, and now here it is, hidden output, dot, so that's the dot product of that times self v plus self v0, and that gives us the output layer input, basically. Okay. And then all we have to do is the output layer input goes through the output activation, which in this case was the softmax. Makes sense, right? It's exactly the same thing we did, and that just gives us YPred. So that's the feed forward. So nothing really special there. Okay. Now we move to the next step, which is going to be the backward pass. Okay, so now we have to go and do the backward pass. Okay. So to understand this one, though, we have to actually have a sense of the loss function, where if you remember, the loss function is cross entropy. So we're going to be using loss now. So if you think, for us to understand backward pass, we have to go back to this, right? We're going to be invoking loss, but whenever we invoke loss, really what we're going to be invoking is cross entropy. And so we need to define cross entropy, which we haven't. So let's actually do that first. Otherwise, it may not make so much sense. So let's go back to cross entropy then. Okay. And here we're going to do, so in cross entropy function, we're going to define whenever we create the object, just going to do define. We're going to init again. So init with 2 of those, self. And we're going to just say basically something like pass or something. So nothing happens. Okay, but we have that function available. And then we need to have within cross entropy a couple of things. So we're going to define 3 functions in here. One function is going to be the loss function. Right? One is going to be the accuracy function. So we're going to need all these mechanisms to be able to evaluate that last part. So as you can see, this is much more complex, and it's starting to look like gradient descent itself, right? So remember, we talked about there's 3 algorithms involved in the training: feed forward, which you saw is just predicting the loss and comparison, backprop, and gradient descent. This is kind of integrating all of these together. Okay, so let's call this one gradient. Okay, so we will need to provide information for all of these. Basically, the idea with this is that we're going to be comparing things. So we're going to be comparing the predicted with the real, pretty much always, right? Because in the feed forward, we predicted, but we also have the real labels. Now we need to compare, look at the difference, and then propagate back. So that's the idea. So the inputs to these 3 functions in the cross entropy are going to be, so obviously we need to put self first, but then after that, y comma p. And then here, self comma y comma p. This one, self comma y comma p. Do you guys see that? So we're doing that, the difference between the 2. So an example of this, the easiest one that I can think of is, let's just do the middle one so that we understand. So we're going to do accuracy. So I can just do return. Now I already defined accuracy somewhere in here, I think, or we haven't actually, but we've done it in other classes where we defined accuracy. So here it should just be return accuracy score, right? Accuracy score between the values in Y and the values in P. Keep in mind, the values in Y and values in P are always returned one hot encoded. We're always getting a vector of, let's say for 3-class problem, because we're taking this as a one hot encoded approach. The label that we get, instead of getting class 0, this is the class. So instead of getting class 0 or class 1 or class 2, we're always getting 1, 0, 0 or 0, 1, 0 or 0, 0, 1, but actually we're getting probabilities, right? We're actually getting, you know, for this one, we probably get 0.80, 0.15, 0.05, right? Remember, because they add up to 1. So we're always getting this. So we would know that this is close to 1, but we need to find that index. The index is 0, 1, 2. So that's why we need to do NP argmax, right? Argmax will give us not the value, but the index of it. So this would return class 0, which is actually what we want. All right, so we're going to need to do that and define it in our code. And we'll wrap up with this for today and then finish this up next class. So if we go back to the code now. All right, so we have accuracy score for these two values here. I'll put in a comma. And then the first value is going to be np.argmax. And then y, right? We need to specify also the axis because it's, you know, could be x and y. So it's got to be not the 0 axis because that's the rows, but the 1 axis, which is the column. Okay. And then we just have to repeat that for p. So that's going to be np.argmax. And this is value p, comma, and then axis is equal to 1. All right, so that's the accuracy score for the two, okay? And then I guess the last thing we can do here is for today is just to find the accuracy score. So let's get that one kind of taken care of, and then we'll pick up on cross entropy in the next class. All right, so let's finish up here. Y true, comma, Y thread, just so that all this comes together. Then we would do accuracy, which is going to be np.sum divided by length of Y true. Could be either one. But this is going to be, we're going to match where Y true is equal to Y pred. So only those that match will return a 1, right? And that will give us then, and we're going to do this, of course, on the axis 0 this time. Axis equal 0. Okay, so that's just the accuracy function. And so that kind of ties into this. In the next class, we need to now focus on the loss function and how that works. It's going to be a type of implementation of cross entropy functions that we saw before, right? The two graphs that one went down and the other one went up. So we're going to make a type of an implementation of that. It's a simplified version. Everything. So I should say this. It's always like the math is always this beautiful thing, right? That looks like this, and you know, but when you actually implement all of that on computers, there's actually something called numerical methods. And what that does is it's always some simplified version of it, you know, because it's faster, because like that math that's really nice, it's impossible to implement it on a computer. You know, like you can't really like actually do an integral, right? It's not possible. You can only approximate it, right, by doing tricks. And so, but the equation will look similar enough to what we saw before. At the end of the day, this is only for your own knowledge to kind of wrap up neural nets. I would not recommend actually doing it. You could literally go into PyTorch or TensorFlow and literally write this up, you know, equation by equation, but it's not recommended because you end up with a lot of nans and things like that. You know, whereas the built-in functions take care of a lot of that functionality for you. Okay, so I'm going to go ahead and save this. You can always and then we're going to wrap this up. We're almost close to the end, so, but you know, it's a lot of information actually to go through it. So we'll continue with this one on Monday, I guess. Clustering will be the last topic. We still have one day. I have that wrap up day, so we should have enough time to look at all the topics. All right, so that's it. I'm gonna go ahead and stop the recording.